Hello, this is Exfixium and welcome to How to Make a Master System Game using Devkit SMS tutorial number 2. In this lesson we go over some basic details of the Sega Master System hardware, how the hardware correlates with programming concepts. We learn a little information about banks and bank switching. We also go over the building blocks of creating graphics for the Master System, detailing information about palettes, tiles, tile maps, and sprite data. Let's dig into it. Okay, I'm going to go over some of the basic information for the Sega Master System. I'm not going to go into extreme depth on the hardware aspects. It's going to go over what will affect us when we go to actually code our game. The first part is the CPU, which is the Zilog Z80, which is the main processor. It's a 3.5 megahertz processor. The VDP, which I'll be using this terminology quite often throughout the upcoming videos, means the video display processor, which is a separate chip from the CPU. The CPU interacts with the VDP through ports, or it sends data to the VDP, and then the VDP processes that data. The underlying chip is a TMS 9918. It's a Texas Instruments processor. And then we have part of that VDP. There's another chip in there, the audio chip, which is the SN76489, which processes PSG music. It's got 4 channels on it. 3 of them are a pulse tone, and then the last channel is a noise channel. The Sega Master System also had another audio unit that was only released in Japan. They had one where you could attach it to the Mark III, or later on it was actually built in to the Sega Master System, and it was the FM2413. This is a frequency modulator add-on or chip, and it basically had instruments, presets. There were 16 of them that you could use as part of your composition, and there was one instrument you could actually customize, so it allowed for different sounding audio out of the Sega Master System. The work RAM or RAM that we'll use is 8K's worth of RAM, which is pretty generous, I think, in my opinion. And we'll definitely be using that, as with Miss Pac-Man. Player 1 and Player 2 have to remember what changes were made on their stage, or the current stage that they're working through. And also because of how big the tile map will be, and we'll explain tile maps in a bit, it was bigger than what the vertical resolution of what the Sega Master System can typically handle. I think it was the original Miss Pac-Man is 288 pixels high, and the Master System typically, well, for our use case, will only be 192 pixels high. So we're going to have to do some scrolling there. We also need to remember what the map is being changed and where we are in the scrolling. So we have to keep that information in RAM, our work RAM, as well as all our game variables. VRAM is 16K, 2 chips that were 8K a pop. So a lot of times we're going to reference the first half of VRAM and second half of VRAM, and that's what I'm talking about here. It's 16K total. CRAM, which is the color RAM, is 32 bytes, and we have 16 colors in our background palette and 16 colors in our sprite palette. We're going to go in more depth when we go to SMS Power and we go over some of the information that a user on there, Maxim, has detailed. So we're going to go through more of that. Along with that, the Master System had a total color palette to choose from of 64 colors. So that's what this is, the total 64 colors that the Master System can actually use or pick from for those 2 palettes. We have paging banks, and we'll definitely touch upon that while we're programming. Everything that we're going to do is going to be paged or banked into these 16K segments, basically. And typically, in our scenario, the first 32K, which will be bank 0 and bank 1, because we're going to start from 0 and 1, will hold our code. Now, if the code is more than 32K, we can actually set up Devkit SMS that we can do code bank switching on bank 1. Or if we know that it's going to be less than 32K, then we can use both these banks and not have to do any sort of bank switching. With Miss Pac-Man, it'll definitely be under that 32K threshold. So we're not going to do any code bank switching in this project. The next 16K is our switchable bank area, where the idea is that if we have resources that are more than what we can do with the addressable memory, what we can do is we can have these banks stored in the ROM that we can take or go to those banks and point to those banks and switch over to them anytime that we need to bring in resources. So like the audio, any sort of graphical resources, all that you can bank into their own little sections that are 16K in size a pop. And the idea is that you can add X amount of these banks and as your project grows or your resources grow, and then as you run through them and code, you bank switch to that bank, you grab that resource to use, and you will see a lot of that. It's very important. Assets to banks, which Devkit SMS supplies, that will play as a huge tool in creating these banks of resources, and then also giving constants and be able to reference them within our code. The VRAM total tiles typically is 448 tiles maximum, and we'll go through that more as, again, when we see what information that Maxim has on SMS Power. And the total amount of bytes for that would be 14,336. And this number becomes important because I'll be using it for when we start writing to VRAM and we want to change the tile map in a certain way, particularly when Miss Pac-Man rolls over a pellet or changes anything on the screen. You want to change that tile and VRAM as she's going along the screen, and you have to update the actual visuals on the screen from when she goes over that tile and consumes that pellet. There's two layers, background layer and the sprite layer. Background layer is a fixed grid of 8x8 pixel tiles. And again, we'll go more into that when we go to SMS Power. So you have your background layer. The tiles for that, when we create a tile map, can actually flip horizontally or left to right, or they can flip vertically or up and down. And then you have the sprite layer, which is a bunch of tiles that can move freely on the screen space. So they move at a per pixel level versus being stuck in a grid, an 8x8 pixel grid. They can move around freely. You can have, again, they can be made of either a single tile, like an 8x8 tile for the sprite, or you can go into what Devkit SMS calls tall mode, where the sprite actually is 8 pixels wide by 16 pixels high, so they're higher in its height, double the tiles. So, and that is a mode that we'll be using. There are pros and cons to using that approach, but in this situation, it's a good choice for this project. And you can have 64 sprites on the screen at one time. There's a limitation as well. BDP allows for 8 sprites horizontally on a scan line, and if it goes over that, then that next sprite will not be displayed. And usually the way that developers get around that is that they alternate which sprites they show on the screen, so that way it's drawn to the screen, but it has like that flicker effect. If you ever seen older 8-bit generation consoles like the Nintendo and like the Master System, they both have this same limitation where they can only show 8 sprites on a horizontal line in a row, and then after that, it doesn't get drawn, so they to mitigate that, they draw alternatively those sprites, so at least they're drawn on the screen, even if it looks like it has that flicker effect. That's basically what it comes to sprites. Master System has some other small quirks when it comes to sprites, but for the most part, since we're using Devkit SMS and we didn't compile it in a way that it's unsafe, it handles a lot of that stuff in the background that we don't have to worry about that. So the advantages of using the SDK. Unfortunately, the sprite layer tiles, or the tiles that the sprites use, they cannot flip in the same way that the background layer can. When you compare it to the Nintendo, it's a complete opposite. So the Nintendo, it cannot flip its background layer tiles, at least as far as I know it can't. But it can flip its sprite layer tiles at any point in time. So having it that you can have sprites on the screen like enemies, your playable character, any sort of graphic on there that moves freely is probably more advantageous than having the background layer be able to flip horizontally and vertically. It still works out for the Master System because it doesn't necessarily need to do any of that stuff where, we have to do a left and right and load it all totally in memory. We have other options. So it's not like the biggest deal, but it would have been nice. Then we have, let's see, so we have that 14,336 bytes total that these tiles can use, and then the rest of the memory towards the bottom of the second half of memory, 2,048 bytes are reserved for the tile map data, which I'll go into further, and the SAT, which is the sprites attributes table, which that's where we define the sprites horizontal and vertical position, as well as the tile that it's using for its graphic. So that's what that information is. And we have hardware scrolling, which is scrolling the map left to right or up and down. There's also another feature that the VDP has where it can hide that first column on the left of the screen. The Master System doesn't have any more VRAM than the 256 pixels wide. So when it goes to scroll left and right, there's no extra room to put the new graphics as you're scrolling. So typically what you do is you would update the first column on the left. You'd update that with your new scrollable tiles, and then depending on if they're going left or right, that's the column you would update, and then it would seem like you're scrolling in world space for quite a lot of map data. So, and we'll go over some of that because the original resolution, as I may have said before, for the Ms. Pac-Man game machine was 288. So we'll have to scroll vertically at least because we only have a vertical resolution of 192, and that's a bit less than the original arcade version. So we'll go through some scrolling there. I'll show you how that's done. For now, let's jump over to SMS Power and go over some of the details that Maxim has given us. As you can see, here we are in smspower.org, Maxim, and how to program. And I feel like these articles that Maxim has put together illustrate exactly how these basic graphical building blocks are used and how they're defined. I'll go over these in brevity, but if you want to know more, I'll leave a link in the description that you can look at these in more detail. So as I said before, the Master System has 2 palettes, 32 colors total. We have to remember though that the sprite palette, the first color, is a transparent color that won't be drawn onto the screen. So technically it's 31 colors really. You could do some stuff halfway through the screen where you can change the palette and do some other things that you could get maybe all 64 colors of the available palette on there. Some even more when I guess some of the combinations that I've seen out there, you might even be able to get some more blended colors out of the 64 colors than is available, which is pretty cool. But we're just talking about your typical use case here. You have two 16 color palettes. You have the background palette. The background layer can use that palette, but you can also make certain tiles the sprite palette as well on the background layer. So it has the ability to use either the background palette or the sprite palette per tile, and each tile can be any one of those 16 colors. So here we have that Maxim has put together here is a numeric representation of what the tile would look like on screen. So the data for this tile has these numbers that index that palette. So the palette starts at 0, ends at 15, 16 colors total, and then each pixel on that 8x8 pixel tile will reference a color. So here, let's go to all the way in the corner one. It's this light green color, so it's 13, and when we look at it on the palette, it's this light color, and that's what actually shows up on the screen. And that's how all the graphics work for the Sega Master System when it comes to tile data. So it's pretty cut and dry. And so this is one palette here. Well, actually it looks like two of them. But the cool thing is that the background palette, when we go to the tile map, we can actually set it either to this background tile, background palette, or again, we can use the sprite palette. And then when we talk about sprites, the sprites cannot do the same thing that the background palette can do, unfortunately. The sprites that only can use the sprite palette, it cannot use the background palette. So there's that information to keep in mind. Here's the total 64 colors that the Sega Master System can use in its palette. Here's the breakdown of the data. So the color space is using 1 byte total. There's some unused bits here, the last two, but here it gives a breakdown of like how many bits for each color. And as you can see, it's only 2 bits per color, so that means that you can only have 4 values total. And then those 4 values that you can use for the RGB space at least is 0, 85, 170, and 255. Those are only color values that are valid for the Master System. If you use any other color outside of it, it will not work. So use these values, and then there's programs out there that can take your images, wherever image editor that you use, and export them so that the Sega Master System can use the image within the game. And the most popular one by far is one that Maxim has put together. It's called Bitmap to Tile. And you could use that to bring in any graphics resources that you want for the game. There's a lot of options there. They also, the biggest thing about it as well is that you can add compression to it. So if your image size is taking too much space or memory or whatever, you can actually compress it down to a smaller size using the built-in compressors on export that Bitmap to Tile allows you to do. So recommend using that for any of your graphical resources. So yeah, there's a list of all the possible colors and their values in certain formats like HTML, RGB. Let's move on to tiles. So that information with the 8x8 pixel tile, that actually gets used within the game in a grid. As you can see here, that Maxim is detailed. Each one of those tiles can be put on this grid to create our visuals for our game. Here it's kind of the same thing that we went over, but not quite. It's explaining how the planar format is being used here to come up with the actual data and the way that it's formatted. This one tile here, this 8x8 pixel tile, is only 32 bytes total when it's loaded into VRAM. Okay, I think that's all we need to go through here. I'm going to move on to tile maps. Tile maps, in a way, is very similar to when we look at the tiles. There's a number that's associated to something on a list. So like with tiles, it was the pixel data that was referenced, kind of like a paint by number. This is sort of the same thing, but instead of pixels, now we're indexing a complete tile. So 0 would be the first tile in our tile set, which would be this blue sky. So as you can see all the zeros here, again, this is a numeric representation of a full screen for the Sega Master System. And we can see that by picking 0, this tile will actually be placed on the screen based off of this. And this whole thing here is called a tile map within the Sega Master System. And again, you just create the screen using these indexes. I will reference one of these. So like here, 39 is this cloud piece. So that will be drawn here, because 0 going left to right until you get here should be 39, starting from 0. And then like this block here would be 1, and then this would be 2 and 3 and 4, and so on and so forth. And you could see like 9, 10, 11, 12 here. This yellow block here, the star tile, that's where that number comes to play, 9, 10, 11, 12, so on and so forth. It's pretty cut and dry. It's the same kind of deal with our actual tile data. One thing to note about each one of these numbers is that they are not bytes, because we still have to be able to get to a value of 511. So the way to do that would be you need to have at least 9 bits to get up to that number. And that's what this, so it's 2 bytes for each one of these values. And the first 9 bits of that is the tile number. So if you count up bits up to 9, it will get you up to a maximum value of 511, 0 to 511 or 512 altogether. So we need to, since our memory, our VRAM, the first half is 256 tiles, and the second half is also technically 256 tiles, but we know that a lot of the, or at least some of the memory, 2048 bytes of it is being used for tile map data, and this is the tile map data in question that we're going to be using in that part, and it's using some of that data for the SAT. So, but we at least need to get a value that's higher than 255, and that's why we have 9 bits here, because we can, with the 9 bits, the maximum value is 512. So if our tile maximum typically is 448, then we need a value that's more than a byte. So if we only have 8 bits, it would be only a maximum value of 0 to 255 or 256 total. So that's the explanation for that first byte plus 1 bit off the next byte. So then for the bits that we use for the rest of the data, we have the horizontal flip flag, which is a 0, 1. It's either saying, okay, you know, we're flipped or not flipped, and that will flip it left or right for that tile. So that will save on VRAM, because you only have to use 1 tile for, say, the left side, and then you just use this flag here, and then it'll automatically, in hardware, flip it. Same thing with the vertical flip, except it's up and down. Palette is what we were discussing before, where we can set this bit to where either it's using the background palette or it's using the sprite palette. Priority is new, and we haven't discussed yet. Priority means that if we set this bit on any one of these tiles, it will actually draw over the sprite layer instead of under. Typically, the background layer is under the sprite layer, but you can have certain tiles that show over top of the sprite if you like. One of the things that needs to be said here is that the first color of whatever palette that the tile is using is considered a transparent color. So if in this instance we make one that, let's say we make this sky tile that it draws over the player, it won't actually draw over the player if all the pixel indexes are set to 0. You'd have to set it higher than 0 for it to actually draw over the sprite. And then at the end we have 3 bits that are unused, but we can technically use them. So the main things that we're talking about here is we're talking about palettes, This is a building block of graphics. It gives us our colors. Then you have the tile or tile set. This is the actual graphical data itself down to the pixel. And then you have the tile map, which is a collection of, or a grid of tiles based off of an ID. So, and it also has some other properties as we discussed here. It's 2 bytes per tile, and this is the information per tile. And this is bitmap to tile. This is a program that you can choose an image or bring an image in, and it will give you options on how to export it. So there's a bunch of options there for if you want it into a sprite format, or if you're using tall sprite format, or if the tile map, if you want to take advantage of the horizontal flipping, vertical flipping, and just a bunch of different things here. You can also edit the information coming in, so you can change the tile map tile map stuff around. You can also change up the palette. I think that's everything we need to cover here. And like I said, next tutorial we'll actually be using a tool to bring in the graphics and to go over some of the details of the stuff we just talked about now. I'm going to try and do it in a visual way. Hope you enjoyed this video, and I'll see you next time.